problem number 40. You have a diagram there of the Earth. The Earth has a radius at the equator of 6.38 times 10 to the 6 meters. And it takes the Earth roughly 24 hours to spin around once. Since it's also revolving around the sun, it's a little bit more complicated. So the actual time of a rotation for 1 day is 23.9 hours. If you convert that into seconds, that's 86,040 seconds. The question is, a person here at the equator, when the Earth is rotating, how fast is their tangential velocity? How fast are they moving tangentially to the center of the Earth? Ultimately, to get that tangential velocity, in the end, what formula do we want to use? In the end, to get that tangential velocity?
RW?
Yes. Ultimately, we're going to use V equals RW. And we know what R is, but bam. But in order to find that tangential velocity, we're going to need to find the angular velocity first. Now, since we know the period, remember that this formula here, the angular displacement over the time, can be also written as omega equals 2 pi radians over the period. So in this case, it's going to be 2 pi radians over 86,040 seconds. And if you crunch that out, what do you get for the angular velocity? 2 pi over 86,040.
It's 86,040 now.
43,020.
Huh?
What's pi over
Doesn't it-
43?
doesn't it-
7.3 times 10 to the negative fifth.
Okay.
Word.
Yeah.
Beautiful. Drop it back.
7.3 times 10 to the
Negative fifth.
negative fifth radians per second.
Yeah.
So that's how fast the Earth is rotating. That's the angular velocity of the Earth.
So you do V equals. Okay.
Imagine if we could all feel the Earth rotating. What would that be?
What would we do with it?
Be cool for a little.
Yeah, I would get a little nauseous. Arthro.
It's like spending your entire life on a swing ride.
I know. It's horrible.
I think we all feel it.
So then if you multiply that out, what do you get for the tangential velocity?
I don't like where I don't like where
A little more than 32 times 10 to the first.
I got 465.7.
What is it?
465. Oh, alright. What is 2 1 again? What is 2 1 again?
465.7 meters per second.
Yep.
So you get to 46.1.
So that's the tangential velocity of the Earth at the equator.
And then the next part of the question asks, at what theta is the tangential speed 1/3 of a person living at the equator?
Yeah. So the interesting thing is, if we draw that dotted line through the Earth here, and that of course should have gone through the center right there. Basically, if you come up here at a certain location up here, the Earth is still rotating at the same angular velocity. So if you come up to this particular point up here, and you want to know, hey, how fast is the Earth rotating? What's the angular velocity? Guess what it's still going to be, no matter where you are on the Earth. It's going to be, where is it? Right here.
65. Bottom.
This guy here. No.
That was our
The-
tangential velocity.
The angular velocity is the same, no matter where you are. But the tangential velocity is going to be different. Because a person standing like right here on the Earth, notice they're going to go around a smaller circle compared to the person standing on the equator. The person on the equator has to go all the way around that big fat circle in about 24 hours. And the person over here has to go through a smaller little circle in 24 hours. But the rotation, the angular velocity, is still the same.
Ow.
So to find
It's like weird to think about.
the
It is.
no, the
No, it's
speed
really
of
weird to think about. It's really weird.
when the tangential speed is 1/3.
Angular velocity.
Wait, if I put this guy on my head, it's not gonna count. Velocity of something.
This is mind-boggling.
No, velocity of the thing is like how like certain parts of the world have more nights or days. Like in a circle.
But the tangential velocity,
Like it's doing. Yeah, I know it's
Top period is that?
so shorter circle. That's going crazy. Yeah.
at the equator, the tangential velocity is the greatest. And as you get closer and closer to one of the poles, your tangential velocity approaches zero. Because if you're standing on the pole right here, what are you basically doing?
You're not really doing
Turning.
anything.
You're
You're
just rotating. But you don't have a tangential velocity.
because there's no radius there.
Because there's no radius there, exactly.
So it's like exponential then?
It probably is going to follow some sort of trig function, some like sine or cosine. So we're going to come up here, and at this point right here, the tangential velocity is 1/3 of that where it is on Ecuador. So it's going to be 1/3 for 65.7. So what is that tangential velocity up there? What's 1/3 of 465.7?
155.3. No, 2.
So this person up here, their tangential velocity is 155.2 meters per second. Yes?
Mm-hmm.
But what's their angular velocity up here?
The same.
The same as before over here, but by 7.3 times 10 to the negative fifth radians per second. So what we can calculate then is this particular radius.
But given that radius, would we know able to know how far north that is of the equator?
Well, that's what I'm hoping.
Oh, okay. Fingers crossed.
Because we know what this radius is too, yes?
Yeah. Because that's like the radius of Earth.
That's the radius of, yes?
That's the equator.
So let's get that R2 and then go back to figure out the angle business. So I'll do a little calculation. I'll squeeze it up here.
What? We want to figure out where the tangential velocity is 1/3 of that on the equator.
Oh, so like at what degree or at like?
I like what latitude.
this is my little R2 up there. So what does that little R2, this guy right in here, turn out to be?
2.13 times 10 to the 6.
That right,
Meters.
2.13 times 10 to the 6 meters. So they want to know the latitude angle. So if we draw a line going up like this, they want to know what this angle is here.
So don't you have to do
As I was saying, what you
Kyle,
need
I
to
don't think you
recognize,
said it.
people.
I don't think you said it.
I swear.
I really don't
Thank
think
you,
so.
Kylie. That this
She
right
literally
here
told me to go. It's
Yeah,
okay,
she
Kylie.
did.
is a radius. I guess we're assuming that the Earth is a perfect sphere.
Yeah. See, that's
Okay.
what I said.
So if
I
that's
said
a
I'd be in
radius,
circles.
this here is a radius.
Ever.
So this radius
I also had a good idea for
is the same as that.
Makes
So
it
that right there is still what?
Kylie.
Six
6.38 times 10
You're
to the
happy with
6
that, right?
meters per second.
yeah,
And then if we know that this up here is 2.13 times 10 to the 6, we can easily find this angle in here, phi, by using which trig function?
Sine.
Sine.
Yeah.
So
Inverse.
sine of phi equals opposite over hypotenuse. So sine of phi
what's
is
B?
going to equal
It's the
phi
other angle.
is going to equal R2 over the whole R. R2 over the whole R.
Kylie, we said that song. We had the same
So what if
conversation
you don't know about like what phi is? How are you supposed to do it?
Well, no, that's
You
just what
don't.
we're calling
I'm
it
just getting
now.
phi so I can get theta.
You need
Because I know they're complementary angles.
Yeah.
Phi plus theta
You
equals
can call
90.
it feet.
So
I
R2
know.
is going to be
So
2.13 times 10 to the 6 meters per second all over
um
6.38 times 10 to the 6 meters per second. So what is phi? The 10 to the 6 cancel out, so it's just 2.13 divided by 6.38. And then take the inverse sine.
Yeah. I was rejected on that.
0.34. Oh no, hold on, I'm in radians.
oh radius.
Yeah.
This is gonna be a long day.
19.5.
Wait a second, wait a second.
Yo, did you see the interview? Interview.
How'd you do that fast?
Wait, was it
Therefore,
19.5?
Such a funny.
what is theta?
70.5.
90 minus 19.5.
We heard each other, like all over the podcast.
And what is it?
Just partners.
70.5.
No, just 70.
70 nothing.
70.5?
Yep.
Yep.
Yeah, I said that.
No, I mean,
Yeah, you
no,
wrote 2.
people don't listen to me.
Yeah,
So
but
I
it's
don't
72.
don't
But,
listen.
Yeah.
Kylie, did you say?
Math, clever.
Sorry.
Yeah, math thing.
That theta right there.